right, this is the friction video. The first question is, how much force would it take to get Bob, this big anvil, to start sliding on the table? So if you're looking at this question, Bob has a weight of 250 newtons. How much force will it take to get Bob to start moving? It needs to be greater than 250, equal to 250, or less than 250 newtons. And here's the hint. What are you pushing against? And are you pushing against its weight or its mass, or is there something else resisting that motion? So what you're going to do is you're going to have the gravitational pull, you're going to have that normal force, you're going to have that applied force that you're trying to push this anvil with, but what's going to be resisting it is going to be that frictional force just to get it to start sliding. Now, friction is a force that always acts in the direction to prevent a sliding action. If no attempt is made to move the object, then no friction acts. So even if you're pushing something and it doesn't move, well, that's what friction is preventing it from sliding along the ground. Now, what is friction? If you zoom in on any surface, even a really smooth surface, you'll notice that there's going to be little surface irregularities. And when two surfaces are being slid against one another, those surface irregularities catch and bump into each other. Now, if you zoom in even further on the atomic level, those surface irregularities, zoom in, and that's going to be like intermolecular forces. But we won't worry about that just yet, but just know that friction is caused by these small surface irregularities. So what affects friction? Well, friction depends on two things and two things only. Number one, the nature and condition of surfaces, and two, how hard those surfaces are pressed together, which is represented by the normal force. So the smoother those surfaces are, the less friction. And if you're going to push two objects together harder, you're going to have more friction. So there are two kinds of friction, static friction and kinetic friction. So static friction is the friction that keeps an object from sliding, that keeps those surfaces from sliding. And the static friction will always match that applied force until you overcome that static friction. There's only so much of a force that static friction can provide before it starts to slide. So if you look at that little animation up there, you'll notice that there is a box. Now that big arrow represents the applied force, and that smaller arrow down at the bottom, that's going to represent the frictional force. And you'll notice as the applied force gets larger, so does that frictional force. It'll match it, but there is a limit. There is a point at which you overcome static friction and it will start to slide. And once it starts to slide, you only have a finite amount of kinetic friction. Now so there are two different types of friction, that static versus kinetic friction. Now kinetic friction will never be greater than static friction. Now what this means is that it's harder to start something sliding than it is to keep an object sliding. So if you watch this brief video, it's gonna show you that it takes about 20 newtons to get this object to start sliding, but once it's sliding, it takes about 14 or 15 newtons to keep it sliding. All right, so there are two equations for friction, one for objects that are not sliding, which is static, and one for objects that are sliding, which is kinetic. So remember that the arrow above some of those forces are going to, or the force, that means that it's a vector quantity. The subscripts, well, one of them, that the N represents the normal force. Now the S means the static friction. Now that U, that's the Greek letter mu, and that is a coefficient of static friction. That represents the nature and condition of those surfaces. And you usually look this up in a table, and you can see there, like, you have two materials in contact. You can have like rubber on concrete dry, rubber on concrete wet. You look these up. These do not have a unit. They don't have a unit. They're not really like an actual value. They're just a coefficient. They're a ratio. So you usually look this up in the table, or you can calculate it. So the normal force represents how hard the surfaces are being pressed together. So, and I always joke around and say, if you need help remembering the equation for friction, remember that friction is fun, right? All right. So let's take a look at something that does not affect friction. Sorry, surface area of contact for rigid surfaces does not affect the amount of friction being applied on an object. So if you look at that top video, you'll notice that it takes about 12 newtons for it to slide. Now, I know that this video is in the way, but you can watch this later. But all they did was they flipped that block vertically, the only thing that changes is the surface area, and it'll take about 12 newtons for it to slide. Now, relative speeds does not affect friction, right? The speed between those surfaces. So notice that in this video, this person is going to be applying the belt sander, and as the speed increases or decreases, notice that it does not affect that frictional force. So on a graph, now notice how when the objects are not sliding, the static friction will equal the applied force. Now there's only a limited number or a limited amount of friction that two surfaces can provide. That is what that equation gives you. Now once those surfaces are sliding, kinetic friction is going to be the same no matter what the applied force is. So if we zoom in on this a little bit more, if we're looking at that bottom part, well, no attempt is made to slide this object. There's no applied force, so there's no frictional force. Now, if we go up a little bit farther, we'll notice that I push a little bit, but I have not overcome static friction. So my frictional force is going to equal the applied force, but opposite in direction. I push a little bit harder. I still have not overcome static friction. So I push harder, and I look at that frictional force. Well, it's going to match it. Now, this point right here, that's the maximum amount of static friction that these two surfaces can provide in this condition, and that can be calculated. Anything more than this, and it will start to slide. Now, kinetic friction, it doesn't matter how hard you push, or if those surfaces are sliding and there's no applied force, kinetic frictional force will bring it to rest, right? It doesn't matter what it is. Like there's only one kinetic frictional force for these two surfaces. Now, does the applied force affect the static friction and or the kinetic friction? So if you notice this, if you look at this, and let's just say a box is being pushed with 50 newtons and the box doesn't slide on the surface, well, no, yet you have not overcome this static friction force. So the magnitude of the static friction is going to be 50 newtons in the opposite direction. Now, let's just say you push a little bit harder with 100 newtons. Well, note it, like you have not overcome static friction. It is not sliding on this table. So it's going to be 100 newtons. So it's going to match it one for one. So the frictional force will be 100 until you overcome the maximum amount of static friction these two surfaces can provide. So what you should get from this is that the applied force affects the static friction force resisting it, right? Once you overcome that maximum amount of static friction, then it's kinetic friction, and it doesn't matter what the applied force is. Even if it's zero, if two surfaces are sliding, kinetic friction force is just going to be the same amount. All right, so you can calculate this. So this is a very simple problem. So a box with a mass of 50 kilograms is being pushed on a level surface with a horizontally applied force. It just starts to slide when 60 newtons is applied and will continually slide slide at a constant velocity if 45 newtons is applied to the box. So the first thing you need to know is the weight of the box, that gravitational pull. So I can plug the weight and the acceleration of all objects on Earth, which is going to be -10. That's what we use. It is -9.81, but we just use -10 to make the math simpler. So plug that in, I'm going to get -500 newtons. So yeah, it's 500 newtons in the downward direction. Now, since it's on a horizontal surface, well, the normal force will be 500 newtons. So now I can come up here and I can calculate the coefficient of static friction. So I know that it just starts to slide when 60 newtons is applied. So I know that 60 newtons is that maximum amount of static friction. So once I plug that in, I can get 0.120. Now remember, it does not have a unit. It does not have a unit. It's just a coefficient. It's just a ratio. All right, so then you can come in here and you can plug that in. So I know that if it's sliding at a constant velocity when 45 newtons is applied, then that's the kinetic friction because it's not accelerating it's not accelerating. So I can plug that in. I can calculate the coefficient of kinetic friction, which is 45 divided by 500. And then you can graph this. So notice that the static friction is a one-to-one relationship all the way up until 60 newtons. And then after that, it's going to be 45 newtons. All right, so in this friction simulation, there's the box that can be pressed and has applied force, and it'll show you that frictional force. So the question is, first you want to calculate the weight of the box. So it's just mass times the acceleration of gravity. Then what is the maximum amount of applied force that can be applied to the box while it's not sliding? What kind of friction is preventing the box from sliding? What is the net force acting on the box when it's not sliding? So you have to do this in the simulation. You have to continually push that box until it starts to slide. And I think it comes to about 125 newtons. And then anything more than that, and it starts to slide because you have not overcome that static friction yet. And as it's not sliding, the net force is zero because it's at rest. Now, as the box is sliding, what kind of friction is resisting the sliding motion? It's going to be that kinetic friction. What is the frictional force being applied to the box? I think the simulation based on this condition is going to be 94 newtons. So then you can calculate the coefficient of static friction and coefficient of kinetic friction based on those numbers. So then you can put that on these graphs. So that point right there at the top of the maximum amount of friction that these two surfaces can provide is going to be 125 newtons, and that kinetic friction is going to be 94 newtons. So then you can draw the free body diagram. You can manipulate the arrows based on these different conditions, whether it's accelerating, constant velocity, slowing down, just what forces are being applied to it, and are those forces balanced or unbalanced. So turn the friction all the way up. What happens to the normal force? Well, that doesn't affect the normal force. That doesn't affect the gravity. So it's not going to affect how hard these surfaces are being pressed together. What happened to the applied force required to start the box sliding? It's going to be more because that maximum amount of static friction has increased. The coefficient of static friction has been increased. So does the applied force affect the static friction and or the kinetic friction being applied to the box? So it's going to affect the static friction. Remember, if you apply 2 newtons, it's going to apply 2 newtons right back. All right. So how can you use your knowledge of friction to survive when your car goes into a skid? So that brings us to anti-lock brakes. So anti-lock brake system uses the difference between static friction and kinetic friction to come to a stop quicker. Well, how does it do this? Well, if your tires begin to slide, the anti-lock brakes release pulse. The brakes it releases the brakes. It pulses the brakes repeatedly to apply the static friction repeatedly. Without anti-lock brakes, the tires are sliding on the ground, and kinetic friction is being applied to the tire to stop your car, which is not as much as static friction. So if your wheels lock up, right, your tires are sliding, and what it does is that's kinetic friction. You can see here that kinetic friction is a lot lower than that static friction. So if you pulse it, that pulse static friction is going to be more than that kinetic friction, and it makes a huge difference. So in a turn, your tires begin to slide. The anti-lock brakes release your brakes to apply that static friction repeatedly. You're going to turn into the skid. You want the tires facing the direction that you want to go, even if it's counterintuitive, like on turns. So you'll notice this animation down there. This person's turning into the skid, even though it's the opposite direction of the turn that it's going. Because once the anti-lock brakes, once that static friction kicks in, you want those wheels going in a direction that you have control. So you turn into the skid, turn towards the direction of the whatever direction the back of your car is going. So this brings us to that hands-on friction lab. So the first thing is asked you about resolution and uncertainty digit. It asks you to find the weight and the normal force of those cylinder, and I think it comes out to 7 newtons. The box should be at rest with the spring scale. So what you're going to do is you're going to slowly pull that cart until it just starts to slide, and that'll give you that maximum amount of static friction. Uh, that'll give you the maximum amount of static friction it takes that you have to overcome. Now, once it's sliding, what's going to happen is it's going to be a less force to keep it sliding at that constant velocity. That'll give you that kinetic friction if you pull it at a constant velocity. So then, based on that, you know the normal force that's based on the weight, and you know the max amount of static friction. Calculate the coefficient of static friction. You can do the same thing for the coefficient of kinetic friction. Then you can put this on this graph, right? And I think it comes out to maybe like 5 and 4.5. That depends on what table or what surface that can change. But I think it's about 5 for that static friction, 5 newtons, and maybe about 4.5 for that kinetic friction. Then, based on that, you can draw the free body diagrams. Think about whether it's accelerating or whether it is constant velocity or rest. Are they balanced? All right. So what would happen to the applied force required to start the box if another 5 kilogram or 0.5 kilogram cylinder was put in the box? What variable does this change? So that's going to change how hard those surfaces are pressed together. Does the applied force affect the static friction and or kinetic friction? Well, that's going to affect the static friction, because the static friction is going to match the applied force to prevent it from sliding. And this last one, the moon has 1/60 amount of Earth's gravity. Imagine this exact experiment were to be performed on the moon with the same table, same box, same metal cylinder, and same spring scale. Would the results of this lab change? Why or why not? Yes, they would change, because that would change that normal force, how hard those surfaces are being pressed together. So this last one is the meter stick one. So what you're going to do is you're going to put the fingers on the ruler at the designated points and slowly move your fingers toward the center. Mark where your fingers meet. Results in the table. So what you should get is that they should meet no matter where you start those fingers. They're going to meet at the same spot. Now, what this is doing is as you're moving your fingers closer, that's changing how hard those surfaces are pressed together. right? Because as you get older, there's more of a weight pressing down. That means there's more of a normal force that's changing how hard they're being pressed together. So if your fingers are moved slow enough, only one finger will slide along the meter stick at a time, while the other finger is stationary. The fingers will then alternate which one is sliding. Explain which one this is. Well, this one's a little bit complicated, but what happens is that as you're sliding it, well, as one finger is sliding, you have kinetic friction. Now, once that kinetic friction gets larger than that max amount of static friction, that stationary one, they'll switch, and it'll go back and forth until your fingers meet in the center. So now let's ask this question. What type of friction allows you to walk across the room? So think about, is your foot sliding? Your foot is not sliding. It's going to be static friction. What happens is you apply a force to the ground. That static frictional force will be applied to you and it'll propel you forward. So could you run faster on a planet with less gravity? Well, could you run faster on the moon? We've already learned that static friction is responsible for being able to walk. We learned that friction depends on two things. If someone were to walk on the moon or another planet, which variable would that affect? It would affect how hard those surfaces would be pressed together. So friction would change on another planet. Like if you were in this building, another one, that would affect that friction because it'll affect how hard those surfaces are pressed together. Now, there are definitely other factors that come into play when we're talking about running in low gravity. And what is the best strategy for taking advantage of the nature of friction when playing the game Jenga? So, which friction provides a lesser force, static or kinetic friction? It's going to be kinetic friction. So, if somebody repeatedly taps the Jenga piece, what type of friction are they applying? Well, if they're starting and stopping it over and over again, that's going to be static friction. So, that's going to just repeatedly pulse that higher static friction, which you don't want in that game of Jenga. It's basically the opposite idea of the anti-lock brakes. So if somebody repeatedly taps a Jenga piece to get it to start over and over again, that person is applying static friction. Now, if someone gets a Jenga piece to move, then keeps that piece sliding, what they are applying that kinetic friction, which is less than that static friction. So you want to apply that lower kinetic friction to get that piece out because you're applying less of a force to that block, less of a force to that tower. So that's what we played. We played Jenga for this, and he answered these questions. What factors, if any, affect the amount of friction being applied to the block? And if a block won't move without tipping the tower over when pushed with an applied force, what variable is causing the static friction to be so large? Explain how this is happening. So what's happening is that that tower might lean over a little bit and it's going to press those blocks together. And that is going to cause that normal force to be how hard those surfaces are being pressed together. When removing a block, at what moment would the applied force of the block be the largest, in turn causing a large force to be applied to the tower? So look at that friction graph. So what it's going to be is the moment it just starts to slide, once you overcome static friction, that's going to be the most amount of force that's being applied to that tower, being applied to that block as well. So the last couple of questions, would it be a better strategy when removing a block from the tower to tap the block repeatedly or remove the block in one motion? Explain your answer. Well, like I've already explained, you want to remove it in one motion because you're applying that kinetic friction more than that static friction repeatedly. And this last one's a little tricky. What would be a better strategy when removing a block from the tower while it is moving? Removing it very quickly or removing it slowly? Or does speed that block is removed even matter? Explain your answer. Well, the relative speed does not affect the amount of kinetic friction. However, what it will do is it'll affect the amount of time that force is applied to that tower. So if you remove it quickly, you're applying that kinetic friction for a very short amount of time. So the best strategy is to, once that block is moving, you keep it moving and you just remove it quickly. That'll provide the least amount of force to that tower. So, final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.